Linear Algebra, a lecture furthering our ideas about vector spaces. So last time we talked about our vector space equipped with two algebraic operations, vector addition and scalar multiplication. In this lecture we will write down exactly what we mean by those operations and spell out some properties of a vector space. A lot of these properties may seem obvious and trivial, but the reason why we're taking the time to go through them is because when we study more interesting vector spaces, it's very important that we're clear in our minds exactly what we mean and what we mean by a vector space, and crucially what we mean by the two algebraic operations acting within our vector space, vector addition and scalar multiplication. So the first up is commutativity of vector addition. This is just a fancy way of saying the order you add two vectors in doesn't matter. So for vectors u and v, u plus v is the same as v plus u. To give you some intuition about this, we can show it in a diagram. If a vector u is, let's say, forward one step, and a vector v is, say, to the right two steps, so that's u and v, we can then also write v plus u. V is to the right two steps, and then u following that is up one step, and quite obviously the result is the same. So vector addition is commutative. The second property is the associativity of vector addition. This is a similar idea as commutativity, although distinct. What associativity says is that if we have two vectors, u plus v, and then we add a third vector, plus w, that's exactly the same as taking v plus w and adding u. There is no difference. Now, we wrote it in this order to make the point that u plus v and then w is exactly the same as v plus w and then u. But understand that because of the property of commutativity, in fact, u plus v plus w is the same as v plus w plus u and a whole plethora of different combinations. Again, these seem like trivial observations, but as we move into more complex vector spaces, they become more important. The third property we want to focus on is that vector space, in a vector space, scalar multiplication is distributive. Again, what do we mean by this? It means for a scalar alpha, these two statements are exactly the same. What's their intuition diagrammatically? Well, let's take, say, a vector u and a vector v. U plus v is this. We're now going to scalar multiply our vector by alpha. The result, alpha u plus v. Now, what we're saying with this property is that that process is exactly the same as taking u and then multiplying by alpha to get alpha u, which is this long one, and then adding alpha v. So here's v, and here's alpha v. The result, the exactly same vector in both cases. The fourth property is the associativity of scalar multiplication, so that alpha beta, two scalars, scalar multiplied by a vector u, is the same as taking beta multiplied by the vector u and then multiplying by alpha. What's the intuition behind this? Well, let's simplify the situation and add some numbers to the equation. Suppose that alpha is equal to 2 and beta is equal to 3, for example. Then for a vector u that looks like this, alpha beta u looks like this. So this is u 6 times. What this property, associativity of scalar multiplication, is saying is that that is exactly the same as taking u 3 times and then taking twice that. Our last two properties relate to, first of all, the zero vector. This has a special property such that 0 plus a vector v is v for all vectors v. The concept of a scalar 1 is such that 1 u is equal to u for all u. Now, what do these two identities relate to? Well, they relate to the two algebraic operations. The zero vector gives us the idea in vector addition of mapping to itself. So we start with v, we apply a vector addition, and we end up at v. Same concept here, but for scalar multiplication. We start with u, we do some scalar multiplication, and we end up at u. What's the intuition behind all these properties? Not that much. The key thing is just to remember these properties to learn. They're fairly basic, fairly obvious,